July 1943. Deep within the fortified walls of the Pentagon in Washington, D.C., a secure room hummed with a profound, almost palpable tension. Engineers and signal personnel, their faces etched with the strain of years, meticulously completed the final connections on a piece of equipment so vast it consumed the entire space, from floor to ceiling, wall to wall. This was no ordinary machine. It was a behemoth of steel, copper, and countless vacuum tubes. Its weight alone, a staggering 50 tons, pressed down on the Pentagon's reinforced floors. It devoured 30 kilowatts of electrical power, enough to sustain a small factory. Yet here, it served a singular, urgent purpose. 13 specially trained operators, each a master of its intricate workings, would be required to bring it to life, to coax its complex circuits into action. Its very existence was the culmination of nearly 3 years of relentless effort, a combined endeavor by some of the most brilliant signal engineers the world had ever known. And its entire monumental purpose was to achieve something utterly unprecedented in the summer of 1943. To make a telephone call that, while intercepted by the enemy, would remain an impenetrable wall of noise, utterly unintelligible. Not the Germans, not the Japanese, not even the most sophisticated signals intelligence operations either Axis power could assemble. Operations that had, by this point in the war, already demonstrated their chilling ability to pluck vital secrets from unsecured Allied voice communications. This machine, a marvel of wartime ingenuity, was christened Sigsaly. The conversations it was built to protect, live, real-time encrypted voice calls between Washington and London, would forge one of the most secure communication links in the history of warfare, a lifeline of strategic command at the very highest level. Winston Churchill himself relied upon its impenetrable shield. Franklin Roosevelt, the President of the United States, spoke through its circuits. The Allied Supreme Command utilized its secure channel to coordinate the intricate strategies that would, ultimately, win the war. Yet, for decades after the final shots were fired, almost no one outside the tightly guarded rooms where these machines resided knew of their existence. By 1942, the Allied High Command faced a paradox. While encrypted text messages and military telegraphs offered a sturdy shield against enemy eyes, fortified by the robust cipher systems of the era, the burgeoning technology of transatlantic voice communication remained a gaping vulnerability. These text-based systems, when properly implemented, offered a reasonable degree of security for written intelligence. The Allies possessed workable solutions for transmitting documents and coded messages. The true nightmare, the Achilles heel of Allied communication, was the telephone. By the early 1940s, transatlantic telephone communication was a reality, a tool increasingly used by senior Allied leaders for its immediacy and perceived convenience. But this convenience came at a terrifying cost. Every word spoken, every strategy discussed, every order given over these lines was, in essence, broadcast to an enemy with an insatiable appetite for intelligence. Sigsaly was the answer to this profound, existential threat, a 50-ton testament to the desperate need for absolute secrecy in a war where every whispered word could turn the tide. Across the vast expanse of the Atlantic, a new marvel of communication had emerged, binding two nations at war with an invisible thread of sound. This was the radio telephone, a sophisticated system that harnessed high-frequency radio waves, allowing human voices to traverse oceans with unprecedented speed. In the darkest hours of conflict, it offered a lifeline. President Roosevelt, seated in the Oval Office in Washington, could speak directly with Prime Minister Churchill in his subterranean war rooms in London, their words crossing thousands of miles in something remarkably close to real time. It was a technological triumph, a promise of instant connection, a tool of immense strategic value. Yet, this very convenience masked a profound vulnerability. The high-frequency radio waves, while carrying the urgent dialogues of wartime leaders, also broadcast them into the ether, an open invitation to any sophisticated listening post within range. And the enemy possessed such capabilities. German interception services, particularly the meticulous operatives of the Deutsche Reichspost and the dedicated stations positioned along the Dutch coast, were not merely capable, they were actively, relentlessly monitoring vulnerable Allied radio-telephone traffic. Their ears were everywhere, their patience boundless, their intent clear. The Allies were acutely aware of this perilous reality. British signals intelligence understood the danger. American counterparts echoed the same dire warnings. This was not a theoretical risk, a distant what if. It was a documented, ongoing operational reality, a constant drain of vital information, a gaping wound in the very fabric of their strategic communications. The knowledge gnawed at them. Every whispered word, every nuanced instruction, every critical decision transmitted across the airwaves might already be compromised. Desperate attempts had been made to staunch this bleed. Before the advent of the system that would define an era, the most widely deployed solution was a device known as the A3 scrambler. Developed in the uneasy years leading up to the global conflict, this voice privacy system had been meticulously installed on the critical transatlantic telephone circuit linking Washington and London. Roosevelt himself relied upon it. Churchill's voice passed through its circuits. Senior military commanders, coordinating the colossal machinery of war, entrusted their most sensitive directives to its supposed protection. But the Germans had broken it. Not partially, not occasionally, not with fleeting glimpses into fragmented conversations. The A3 scrambler had been comprehensively, devastatingly compromised by German interception specialists. Along the windswept Dutch coast, a dedicated German intercept station meticulously recorded the scrambled Allied voice calls, while brilliant German engineers, working with chilling precision, systematically unscrambled them. Conversations between the Allied leaders, intimate exchanges about grand strategy, the intricate details of operational planning, the high-stakes calculus of Allied decision-making, all were laid bare. The mere act of scrambling, once a symbol of security, now offered no defense. It was a devastating betrayal, a silent infiltration into the very heart of the Allied command. The discovery of this catastrophic breach sent shockwaves through the Allied intelligence apparatus. The implications were too profound, too dangerous to ignore. A stopgap measure, a minor improvement, an enhanced version of the A3 scrambler would not suffice. The situation demanded a fundamental solution, something categorically different, a system built upon an entirely new security foundation. It had to be immune to the sophisticated analytical attacks that had so thoroughly dismantled every previous voice-scrambling approach. The stakes were nothing less than the course of the war itself. This urgent, seemingly insurmountable requirement landed squarely on the desks of the brilliant minds at Bell Telephone Laboratories in New York. The challenge they faced was immense, a crucible of intellectual and engineering might, and from it emerged one of the most remarkable technological achievements of the entire war, a testament to human ingenuity under unimaginable pressure. At its core, the fundamental engineering challenge that had defeated every earlier voice encryption system, and the reason its solution proved so extraordinarily difficult, lay in the very nature of sound itself. Voice is inherently analog. When a human speaks, the vocal cords and mouth create a continuously varying sound wave, a delicate tapestry of pressure fluctuations in the air. These variations are fluid, infinite in their subtle gradations, lacking discrete boundaries. Imagine the smooth, unbroken curve of a sine wave, or the nuanced brushstrokes of a master painter. There are no sharp edges, no distinct steps from one point to the next. Every slight shift in pitch, every subtle change in volume, Every unique inflection creates an almost limitless spectrum of auditory information. This continuous, unbroken flow of data is precisely what makes analog signals so challenging. Analog voice resists such precise dissection, presenting an encryption puzzle of unparalleled complexity. The task was not merely to obscure a message, but to fundamentally transform the very essence of human speech into something utterly unrecognizable, yet perfectly reconstructible, without leaving a single trace for enemy ears to exploit. The human voice, a marvel of biological engineering, begins as mere vibrations. Air, expelled from the lungs, causes vocal cords to oscillate, creating pressure variations that ripple through the atmosphere. A telephone, in its elegant simplicity, captures these subtle undulations, translating them into a continuously varying electrical signal. This invisible current then embarks on a journey, traversing vast distances along a wire or through the ethereal pathways of a radio channel. At its destination, a speaker reverses the miracle, transforming the electrical impulses back into the familiar, intricate tapestry of sound. For centuries, the challenge of securing information in transit remained largely confined to the written word. Encrypting a telegraph message, for instance, presented a problem of a fundamentally different order. One takes discrete units, individual letters, numbers, or symbols, and subjects them to a carefully orchestrated transformation. These units are either substituted, each for another, or rearranged into a new sequence, all governed by the precise logic of a cipher key. The result is a new, seemingly nonsensical set of discrete units. Yet, armed with the identical key, a designated recipient can meticulously reverse the process, restoring the original message to its pristine clarity. The underlying mathematics, while intricate, remains manageable because the information exists in distinct, separable pieces, each segment a self-contained entity awaiting its specific manipulation. Encrypting live voice, however, plunges into an entirely different category of problem. Here, the challenge is not one of discrete units, but of an unbroken, continuously flowing analog signal. Imagine a wave, constantly shifting, perpetually evolving, carrying the nuanced inflections and subtle cadences of human speech. This wave must be transmitted in real time, its integrity preserved, and it must arrive at its destination in a form instantly convertible back into intelligible speech. The very nature of conversation dictates an absolute immediacy. The listener cannot endure a delay, cannot wait for an entire message to conclude before the decryption process even begins. Every fleeting fraction of a second of audio demands simultaneous encryption, transmission, and decryption. The flow must be seamless, invisible to the ear. The early architects of voice security, those who engineered the scramblers preceding the advent of truly robust digital systems, grappled with this continuous flow by primarily manipulating the frequency components inherent in the voice signal. Their approach involved dissecting the audio into distinct frequency bands, then shuffling or inverting these bands according to a predetermined pattern. The A3 scrambler, a device once considered state-of-the-art, employed precisely this method. Indeed, most serious competing systems of that era adopted similar strategies. Yet, despite their ingenuity, all these systems shared a profound and ultimately fatal vulnerability. Human speech, regardless of its speaker or language, possesses an inherent statistical architecture, a complex web of patterns that prove extraordinarily difficult to completely obliterate through mere frequency manipulation. Even when a heavily scrambled T obvious features, but rather persistent regularities in how acoustic energy is distributed across different frequencies, or predictable patterns in how the signal subtly changes over time. A sophisticated analyst, armed with sufficient skill and an ample collection of intercepted material, could painstakingly exploit these residual patterns. The Germans, in their relentless pursuit of intelligence, did not break the A3 scrambler through a stroke of luck or the fortunate acquisition of a stolen key. Their success was far more profound, a testament to rigorous cryptanalysis. They shattered its supposed security because analog scrambling, by its very design, merely obscured the signal. It twisted and distorted the information, rendering it unintelligible to the casual listener. But it did not genuinely encrypt it. The fundamental, exploitable patterns remained, however deeply buried. What the world desperately needed was a system built upon a mathematically unassailable security foundation. A paradigm where an intercepted signal, without the precise correct key, would yield absolutely no recoverable, usable information about the original voice content. It required a transformation so complete that the scrambled output became an impenetrable wall of pure, meaningless noise, utterly devoid of any lingering echo of the human voice it once carried. The year is 1942. The world is ablaze, consumed by a war of unprecedented scale and technological ferocity. Amidst the chaos, a desperate need arose: absolute, unbreachable secrecy for the most vital communications between allied leaders. The very fate of nations hinged upon it. A theoretical foundation for such security existed, a concept whispered in the most guarded cryptographic circles: the one-time pad. In the pristine realm of pure mathematics, the one-time pad stood as an unassailable fortress. It was not merely difficult to penetrate, nor computationally expensive to overcome. It was, quite simply, genuinely impossible to break, provided it sage any message and combine it with a truly random key. This key had to be exactly the same length as the message itself, used only once and then discarded forever. The resulting ciphertext, a seemingly chaotic jumble of signals, contained no exploitable information, no discernible pattern, no mathematical shadow of the original message. Without the precise, identical key, any attempt at analytical attack, any effort to reverse engineer the plaintext, was utterly futile. The message remained locked away, impervious to even the most brilliant minds. But the chasm between theoretical perfection and real-world application, especially in the crucible of wartime, was vast. To adapt this abstract principle to the dynamic, continuous flow of real-time voice communication in 1942 demanded a leap of engineering faith, a series of interconnected challenges that had never before been conceived, let alone conquered. This was not a matter of refinement. It was an act of creation, forging an entirely new technological paradigm from the ground up. Enter the brilliant minds at Bell Labs. Under the visionary lead-monumental quest, they faced not a single obstacle, but a complex, interlocking chain of problems, each demanding an unprecedented solution, and they set about solving them all, simultaneously, in a race against time and the enemy's eavesdropping capabilities. The sheer audacity of their undertaking is difficult to grasp today. They were not merely building a machine, they were inventing the very principles upon which it would operate. The staggering scale of their eventual triumph, the sheer weight of their innovation, manifested itself in a device known as Sigsaly, a 50-ton colossus of wires, tubes, and relays. Its immense physical presence was a direct reflection of the intellectual and engineering hurdles overcome. To truly comprehend Sigsaly, one must trace the intricate path of its creation, understanding it as a meticulously constructed sequence of engineering triumphs. Each problem solved laid the indispensable groundwork for the next, forming an escalating cascade of innovation. The first fundamental hurdle was the inherent nature of speech itself. A one-time pad, by its very definition, operates on discrete values, distinct numbers, specific characters, quantifiable units that can be combined mathematically with key values. An ordinary voice signal, however, is not discrete. It is a continuous, undulating wave, a fluid stream of sound pressure variations that ebb and flow without sharp breaks or defined steps. One cannot simply overlay a random sequence of numbers onto a continuously varying analog wave and expect cryptographic integrity. The very medium defied the method. Applying a one-time pad directly to such an analog signal was an impossibility, a square peg in a round hole of the most profound technical magnitude. The ingenious solution devised by the Bell Labs engineers was a radical departure from conventional thought. Before any encryption could even begin, they had to transform the useful information embedded within the voice signal into a digital representation. This was not the raw waveform digitization familiar to modern telephone systems, where the entire sound wave is sampled and converted into a stream of bits. Instead, their approach was far more sophisticated, a prescient glimpse into the future of speech processing. They meticulously analyzed the speech, breaking it down into a set of underlying parameters. These parameters, rather than the raw wave, could then be sampled, precisely measured, and mathematically processed. This groundbreaking process stood at the very cutting edge of what would eventually be recognized as digitization. In 1942, it was far from a routine engineering procedure. It was a bold foray into an uncharted research frontier, pushing the boundaries of what was technologically feasible. The theoretical underpinnings for this revolution had been laid years earlier, in part by Harry Nyquist himself, working at Bell Labs in the late 1920s. Nyquist had articulated the profound principle that a continuously varying signal could, indeed, be accurately represented by a series of discrete samples, provided those samples were taken at a sufficiently high and consistent rate. Yet translating Nyquist's elegant theoretical framework from the abstract world of equations and diagrams into robust working hardware capable of processing human speech in real time under the immense pressures of wartime presented an entirely different order of challenge. It required not just intellectual brilliance, but an unparalleled blend of practical ingenuity, relentless experimentation, and an unwavering commitment to a vision that few could even conceive. The journey from concept to operational reality was fraught with countless unforeseen complexities, each demanding innovative solutions that would redefine the very landscape of secure communication. And so, the 50-ton Leviathan began to take shape, a tangible manifestation of an unbreakable promise forged in the crucible of war, securing the voices that would shape history. In the crucible of global conflict, the very act of spoken communication became a perilous gamble. The challenge was monumental: to render human voice utterly indecipherable to any unauthorized ear, yet perfectly clear to its intended recipient, all in real time, with the technology of the 1940s. Direct digitization of a raw voice signal, as we understand it today, was an impossibility, a technological chasm too vast to bridge. Sigsaly's engineers, visionaries operating at the very edge of what was conceivable, conceived a radical departure. They built a system not to replicate the voice, but to dissect it. Their innovation was a vocoder-based architecture, an intricate machine designed to analyze the incoming voice signal, extracting its fundamental, defining parameters rather than attempting to capture its full, complex waveform. Imagine the human voice, a symphony of frequencies and inflections, reduced not to a crude digital replica, but to its bare, essential architecture. The system meticulously sampled the energy present across 10 specific frequency bands, doing so 50 times every single second. Alongside this granular frequency data, it captured additional parameters representing the speaker's pitch and the unique character of their speech. These meticulously extracted parameters were then transformed into digital values, into pure numbers, ready for the rigorous mathematical property. This singular engineering decision stands as one of the most profound and audacious choices in Sigsaly's entire design. It marked a philosophical pivot, Instead of grappling with the insurmountable task of encrypting the full analog complexity of a voice waveform, the system intelligently distilled the voice down to its absolute informational essence. It isolated precisely those parameters that a listener's ear instinctively uses to comprehend speech. And it was only this essential data that was subjected to the crucible of encryption. The consequence was a deliberate sacrifice of audio naturalness. The resulting voice quality was undeniably mechanical, artificial, almost robotic. Yet within its stark, unembellished cadence lay perfect intelligibility. And crucially, without the precise corresponding key, the garbled output remained an impenetrable wall of noise, a meaningless jumble of sounds. The price of security was a voice stripped of its warmth, but imbued with an unparalleled resilience. But even the most ingenious encryption is only as strong as its key. This fundamental truth led Sigsaly's designers to confront a challenge that transcended mere engineering, delving into the very philosophy of randomness. For a one-time pad, the bedrock of Sigsaly's security, to be truly unbreakable, its key had to be genuinely, unequivocally random. Not pseudo-random, not a sequence generated by an algorithm designed to mimic randomness, but ultimately predictable through mathematical determination. It demanded true randomness, where each value within the key sequence was statistically independent of every other, devoid of any discernible pattern that even the most sophisticated mathematical analysis could exploit. Generating numbers of such pristine, unassailable randomness in hardware at the speed required to key a real-time voice stream in 1942 was an unprecedented technical hurdle. It was, quite simply, an unsolved problem on the global stage. Yet, within the hallowed halls of Bell Labs, a solution emerged from an unexpected source, a testament to the era's ingenuity. Engineers harnessed the inherent unpredictability of wideband electronic noise, a chaotic symphony generated by large mercury vapor rectifier vacuum tubes. These industrial-grade components, typically used for power-convected chaos and meticulously converting it into coded values. The Sigsaly team forged key material that for all practical purposes possessed the genuine randomness necessary to uphold the uncompromising security of a one-time pad. These precious keys, these ephemeral strings of pure unpredictability, found their tangible form on large phonograph discs. Each grooved surface held approximately 12 minutes of random key material, a precious cargo of silence, poised to unlock or obscure the most vital communications. Matching copies of each key segment were painstakingly manufactured, one embarking on a clandestine journey to Washington, the other dispatched across the perilous Atlantic to London. To initiate a secure conversation, both ends of the communication chain engaged in a precise, almost ceremonial ritual. They would load the identical key record onto their respective machines and, with synchronized precision, commence playback at the exact same moment. The random noise etched into the record, meticulously converted into a stream of numbers, became the one-time pad key. It was this singular, unpredictable sequence that encrypted the processed voice data parameters at one end and, with mirror image fidelity, decrypted them at the other. In an era defined by shadow and uncertainty, Sigsaly offered not merely a secure line, but a profound testament to human ingenuity. It transformed the very essence of voice into an unbreakable whisper, safeguarding the most critical dialogues of a world at war, all through an audacious blend of technological foresight and a deep, almost philosophical understanding of information itself. Every whisper, every command, every agonizing decision uttered through the secure lines of the Sigsaly system was treated as if it were the last. The moment a conversation concluded, the physical records, the very essence of the encryption key, were incinerated. They vanished, leaving no trace, never to be reused. This was the absolute, unyielding adherence to the one-time pad principle, a guarantee of cryptographic invulnerability that demanded a relentless, almost ritualistic destruction after each use. Yet, beyond the meticulous obliteration of evidence lay an engineering challenge so profound it consumed the ingenuity of a generation: synchronization. It was a silent, invisible battle for perfect alignment, a ghost in the machine that became a primary driver of Sigsaly's colossal size and bewildering complexity. For the intricate dance of decryption to unfold, both ends of the transatlantic conversation had to operate in a state of absolute, instantaneous harmony. The key record spinning in a secure room in Washington and its counterpart in a bunker beneath London had to process the identical key value at the precise, infinitesimal fraction of the same second. Not merely close enough, not almost, but exactly. Even the slightest deviation, a temporal drift of a mere microsecond, would shatter the illusion of communication. The decrypting hardware, combining voice data with the wrong segment of the key, would produce not intelligible speech, but a cacophony of garbled static, an impenetrable wall of noise. The entire monumental effort would collapse into electronic gibberish. Maintaining this surgical precision across a vast ocean where radio signals battled atmospheric interference and unpredictable propagation delays, where the very path through the ionosphere was a shifting, imperfect medium, presented an almost insurmountable obstacle. Two physically disparate machines, running independently on different continents, needed to beat as one. This demanded a timing system of unprecedented sophistication, a marvel of electromechanical engineering. Sigsaly engineers confronted this challenge head-on. Their solution was a symphony of meticulously calibrated components, precision timing equipment, some of the most accurate turntables ever conceived, and rigorous startup procedures based on pre-agreed reference times. Operators, their nerves taut, would then make minute, almost imperceptible phase adjustments, coaxing the two distant ends into perfect, crystalline alignment. This intricate synchronization apparatus alone accounted for a substantial portion of the equipment's physical bulk and its almost mythical complexity. Then came the fourth, equally formidable hurdle: transmission. The highly sensitive, encrypted digital signal had to traverse the vast expanse of the Atlantic via radio, a medium inherently hostile to such precision. Radio transmission introduced its own unique set of engineering nightmares. The signal itself was an alien entity. It moved through multiple channels, employing advanced frequency shift techniques, but its character bore no resemblance to ordinary human speech. It was a raw digital stream, a fragile pulse of data that had to survive the brutal distortions of long-distance wartime transmission. It needed to arrive at its destination in a form pristine enough for the decryption hardware to process with unwavering accuracy. This demanded a meticulous engineering of signal levels, a precise allocation of bandwidth, and an inbuilt tolerance for the inevitable imperfections of real-world circuits. Every nuance, every fluctuation in the radio path threatened to corrupt the vital data. At the receiving end, the process reversed with equal delicacy. The hardware had to meticulously disentangle the encrypted channels, apply the perfectly synchronized key, and then reconstruct the speech parameters with enough fidelity for the vocoder to synthesize an understandable human voice. From the initial vocoder encoding, through the precise quantization of speech, the synchronized playback of the key, the perilous transatlantic transmission, and the final intricate voice reconstruction, every single one of these disparate, complex systems had to operate in flawless concert. They had to function simultaneously, in real time, without the slightest hint of failure. For in the crucible of global conflict, the stakes were too high for anything less than absolute, unbreakable communication. A cavernous room, purpose-built and bristling with technology. 40 racks of equipment, each towering, humming with unseen power. 50 tons of electronics, motors, and precision mechanical components, all encased in a labyrinth of wires and steel. This was not merely a machine. It was an architectural marvel of wartime ingenuity, a silent behemoth demanding its own dedicated ecosystem. Special air conditioning systems worked tirelessly, battling the immense heat generated by its ceaseless operation, a heat so intense it would render the space uninhabitable without constant intervention. This colossus, this monumental secret, was Sigsaly. The first operational Sigsaly terminal found its home deep within the Pentagon, a fortress of American power in Washington, D.C. In the middle of 1943, it formally entered service, a clandestine heart beating at the very core of the Allied war effort. Across the Atlantic, its counterpart resided in an equally unexpected location, the subterranean complex beneath Selfridge's department store on London's bustling Oxford Street. A stark contrast to the Pentagon's official grandeur, this choice underscored the system's critical requirements. Its protected underground space offered the necessary security and the sheer physical volume to house a machine of such unprecedented scale and strategic importance. Above, shoppers navigated the wartime shortages. Below, history was being forged in encrypted whispers. Washington held the first, London the second. The network began to spread, a web of impenetrable communication stretching across the globe. A third terminal was swiftly installed in Algiers, providing vital support for Allied operations across the Mediterranean theater. The expansion continued, driven by the relentless march of war and the desperate need for secure dialogue. Terminals emerged in Brisbane, a strategic hub in the Pacific; in Hawaii, guarding the vast ocean; in Oakland, a gateway to the American West. After the liberation of Paris, a Sigsaly terminal arrived, symbolizing renewed hope and the re-establishment of critical links. Further into the Pacific, Guam and Manila became home to these vital installations. Even after the war's conclusion, the system's importance persisted, with new sites appearing in Frankfurt, Berlin, and Tokyo, reflecting the shifting geopolitical landscape. One terminal even embarked on a nomadic existence, installed aboard a 250-ton lighter, providing a mobile Sigsaly capability that traversed the vast, contested waters of the Pacific. By the time this extraordinary system was finally retired, 12 Sigsaly terminals had been strategically placed across the entire Allied and post-war operational theater, each a node in a secret global conversation. Operating and maintaining each terminal required an elite cadre, a dedicated team of specially trained operators, engineers, and technicians. They possessed not just technical aptitude, but an intimate, almost intuitive understanding of the equipment's intricate operation and demanding maintenance requirements. These individuals were hand-picked, their expertise a rare commodity, their loyalty unquestionable. Their security clearances were of the highest possible level, a testament to the profound sensitivity of their work. The very existence of Sigsaly was classified with such ferocity that the vast majority of people who walked past the unassuming rooms housing these terminals had not the slightest inkling of the world-altering secrets being exchanged within. The silent hum behind those locked doors remained an enigma, a whisper unheard by the world outside. The operational security surrounding Sigsaly reached almost legendary proportions. Every piece of equipment, every component was handled under a shroud of extreme secrecy. Personnel assigned to the project signed agreements that bound them not only to silence regarding the operational details, but more profoundly, to deny the fundamental fact of the system's existence as channel. The capability remained a phantom, meticulously hidden behind the mundane routines of wartime communications bureaucracy. Throughout the pivotal latter stages of the war, Sigsaly served as the indispensable conduit for the highest-level Allied communications. It facilitated the coordination of major strategic decisions, shaping the very fabric of the conflict. Plans for Operation Overlord, the monumental invasion that would turn the tide, were forged through its secure lines. Discussions about the relentless strategic bombing campaign, designed to cripple the enemy's industrial might, flowed through its circuits. Even in the immediate aftermath of D-Day, the crucial deliberations regarding the pace of the Allied advance through France relied upon its unparalleled secrecy. This monumental machine, born of immense scale and shrouded in an impenetrable veil of secrecy, did not merely witness history. It was the silent, unseen architect of its most critical turning points. The fate of nations, the very trajectory of the Second World War's final, brutal phases in Europe, hung suspended within a series of secure rooms. Each of these formidable spaces weighed approximately 50 tons, a colossal mass of machinery dedicated to an unprecedented task. Within their shielded confines, the highest-level conversations unfolded, decisions were forged, and strategies were honed. And through it all, the enemy, for all their formidable ingenuity, could never penetrate the veil. This impenetrable shield was no mere stroke of luck, no accident of war. The German intelligence apparatus was a relentless, sophisticated force, their interception services among the most advanced in the world. This was the same adversary that had previously shattered the security of the A3 scrambler, a testament to their cryptographic prowess. They maintained their relentless vigilance throughout the entire conflict, their listening posts spanning the continent, constantly sifting through the cacophony of wartime radio traffic. German intercept stations, vast networks of dedicated operators and cutting-edge equipment, recorded every vulnerable signal they could seize from the airwaves. Yet, when their sophisticated systems managed to latch onto a SIG-SALY transmission, the results were consistently, utterly baffling. From their perspective, the intercepted data was nothing short of useless. It was not merely scrambled speech that retained the telltale, organic fingerprints of a human voice, awaiting a clever analyst to unravel its patterns. Nor was it a conventional cipher, a puzzle that could be reversed with enough computational power or cryptanalytic insight. What they captured was an alien torrent of encrypted channel traffic, protected by a revolutionary one-time key material and an exacting demand for perfect synchronization. It was a digital ghost, a stream of data that yielded absolutely nothing intelligible, no tactical advantage, no scrap of intelligence for the entire duration of the war. Their finest minds, their most advanced machines, all were defeated by a silence that spoke volumes. A one-time pad, when implemented with absolute precision, is not merely a difficult puzzle to solve. It is, by its very nature, an absolute wall. The Germans painstakingly recorded every fragment of SIG-SALY traffic they could detect. They subjected it to every known method of analysis, every theoretical attack, every desperate attempt to find a weakness. Yet, they gleaned nothing. The system remained an enigma, a source of profound frustration, its secrets locked away. So profound was its security, so revolutionary its design, that SIG-SALY remained shrouded in the highest levels of classification for decades after the last shot was fired. The full, intricate details of its operation, the elegant one-time key approach, the groundbreaking vocoder-based speech analysis, the ingenious physical generation of truly random noise for key material. None of these were ever allowed to fall into enemy hands, nor into the public domain. It wasn't until 1976, a full 31 years after the war's conclusion, that the United States government finally declassified the program. When the world's cryptographic and communications engineering communities were at last permitted to examine the astonishing achievement Bell Labs had engineered in 1942 and 1943, the reaction was not merely significant, it was one of profound awe. This astonishment did not stem from the revelation of an entirely unknown theoretical framework. Parts of the underlying principles were already understood by specialists, nascent ideas floating in academic circles. The true marvel, the source of their collective wonder, was the sheer audacity and foresight of its practical implementation. In 1943, under the immense pressure of global conflict, SigSally had brought into being a fully functional, secure digital speech transmission system. To grasp the magnitude of this achievement, consider the timeline of civilian technology. The commercial telephone networks, the sprawling Bell system, did not even begin offering pulse code modulation, or PCM, service until 1962, leveraging T-carrier technology. Widespread digital voice transmission, the ubiquitous standard we know today, arrived even later. Yet, SigSally had accomplished this feat under the most demanding wartime conditions, relying on the bulky, heat-generating vacuum tube technology of the 1940s, long before the civilian world could even conceive of making anything remotely comparable a routine reality. Those 50 tons of equipment filling those secure rooms were far more than just an emergency wartime solution. They were a visionary leap, one of the very first working prototypes of secure digital speech in the modern world. Born from the crucible of conflict, these colossal machines did not just safeguard the critical conversations that decided a war. They quietly laid the foundational stones for the secure, interconnected digital age we inhabit today. A whisper across continents. A voice, digitized, encoded, fragmented into a stream of data, then reassembled flawlessly in mere milliseconds. This invisible alchemy, this seamless translation of sound into secure information, unfolds within a microchip smaller than a human fingernail, every time a call connects through a mobile network or a digital application. Yet, just over 80 years ago, the very same fundamental feat of secure voice communication demanded an entirely different scale. Imagine a cavernous room, not a chip. A space filled with the rhythmic hum of thousands of vacuum tubes, the precise whirring of dozens of motors, the delicate rotation of custom-cut phonograph records, all orchestrated by a dedicated team of engineers. This was SigSally, a colossal marvel of wartime ingenuity from 1943, weighing an astonishing 50 tons. The sheer mass of SigSally, its monumental footprint, was not a testament to inefficiency. It was a testament to groundbreaking innovation forged under the most extreme pressure. The brilliant minds at Bell Labs were charting entirely new territory, inventing solutions to problems that had never before been conceived, using only the materials and technologies available to them. There was no luxury of slow, civilian miniaturization. The exigencies of global conflict demanded immediate, working solutions, regardless of their physical dimensions. They confronted and conquered every major engineering hurdle, their brilliance yielding solutions that, at the time, simply required an immense amount of hardware. This pattern echoes consistently throughout the history of military-driven technology. The initial working solution to a genuinely novel problem is almost invariably colossal, prohibitively expensive, and utterly impractical for widespread deployment. The second generation invariably shrinks, becoming more manageable. By the third, it achieves true portability. And by the 10th iteration, that once monstrous invention fits comfortably in your pocket, becoming an indispensable part of daily life, used without a second thought. SigSally's story is also a profound lesson in the true meaning of security. It illuminates why genuine cryptographic strength matters infinitely more than mere inconvenience. Consider the A3 Scrambler, a system designed to foil casual eavesdroppers, difficult enough to deter many. Yet the German cryptanalysts, relentless in their pursuit, ultimately broke it. SigSally, by contrast, was built upon a fundamentally stronger, mathematically robust foundation. The Germans never broke it. The distinction between very hard to crack and cryptographically sound is not a subtle academic point. It is a chasm. In the brutal context of a world war, this difference was not a matter of style or preference, but of consequence, of lives saved or lost, of the very outcome of history. Modern cryptographic systems, the invisible guardians protecting your bank transactions, your private messages, your most sensitive medical records, are constructed upon the same bedrock principles. They rely on sophisticated mathematical algorithms and meticulously analyzed security assumptions, precisely because the lessons of Sigsaly and its less fortunate predecessors endure. The failure of the A3 scrambler taught the world that obscurity alone is never enough. The unwavering success of Sigsaly demonstrated unequivocally that mathematics and engineering, when applied with rigorous precision, can indeed build an unbreakable shield. That is the enduring legacy of 50 tons of equipment, meticulously guarded in secure rooms in Washington and London. A silent, powerful testament to the hidden decisions and profound engineering insights that shaped the modern world. A legacy you encounter and rely upon every single day.